I'd like to thank the organizers of this symposium for asking me to give this talk. And I would like to especially thank Sunil Kumar, who has been my host here. I'm spending my sabbatical this semester. And it has been really a lot of fun meeting with faculty members in physics and the soft matter group, as well as students and postdocs at IIT Madras. And it's very nice to see the very good amount of good work being done here and other parts of India. Okay, so I'll be talking about some recent results we obtained on collective motion of particles in confinement. And it's something that actually I don't have prior expertise in. I've done a lot of work on soft matter, but not really on active matter. But with the collaboration of Sunil, it has been a very interesting, very nice journey to learn about these systems. So the collaborators in this work, besides Sunil, are Chen-Hui Peng, who used to be a faculty member in my department, but for some reason for some family reasons, he went back to China. And two graduate students, Haosheng Wen and Yu Zhu. So of course, as Adam and many others before, fish or flocks, or sometimes called murmurations of birds that are starlings. And actually in a park in Memphis, it's very common to see this just before evening, as well as like floating bridges of ants, and some mammals also create some kind of self-assemblies on water. So that's kind of large-scale collective behavior found in nature. But you can also find one can find collective behavior of active systems at a much more microscopic scale. For example, these are eukaryotic cells that do self-assemble. I mean, we can think of tissue, for example, as some self-assembly, and the cells, of course, are active there. And this organization is important to many physiological functions, as well as kind of pathological situations like metastasis. And we can also observe collective behavior, of course, in bacteria, which are used by bacteria for many purposes, such as reduction in competition for food, or to help them accelerate kind of growth faster, and also to survive under kind of difficult or under difficult environmental circumstances. And even at the more microscopic level, such as within the cell, one can see interesting active organization, for example, of actomyosin. And these are or could be important for also many functions within the cell itself that allows it, for example, to move or help in cell divisions or various within the cell. So active matter systems exhibit kind of a generic spatio-temporal behavior or coherence, which is typically manifested by clustering of the units that make up your system and the collective kind of motion of the particles or the units. And so because there is this generic behavior, as physicists in general, we look at these systems and try to think about the kind of general principles that allow for this kind of behavior. And that, of course, in a theoretical kind of point of view, have been developing model with minimum number of kind of parameters. Okay, so the parameters that affect the collective behavior of self-propelled particles are the kind of detail of the at the unit level, the details of the motion of the particle. Of course, packing fraction or density is important. The nature of interactions or coupling between neighboring particles is also important. Spatial dimension can be important. And of course, another parameter that is very important is the environmental details. These can correspond to the geometric confinement, the boundary of the system, for example, whether there are obstacles in the system, what's the geometry, or how are these obstacles distributed in the system. The details of the medium, whether the medium is just a Newtonian fluid, or it's a viscoelastic system, or it's a kind of a liquid crystal system, order in it, those could be all important. And a lot of scientists have been looking at these environmental effects on the collective behavior, particularly the last few years. And that's kind of what I will focus on mostly. So these are just examples of the effect of, for example, here, confinement on the behavior. These are active Brownian particles. So in the case where there is no collective motion, the system is just thermal, then the particle will just be distributed more or less uniformly in the system. So what you see here is actually the trajectories of particles. And if there is some kind of some activity, then there is an increase in the kind of density of the particles near the boundary of the system. And if the activity is large, then most of the particles just are stuck at the boundary. They may move around, but they are not going to explore really the interior of the system. Another interesting example of an environmental kind of effect on collective behavior in active matter is obstacles. So these are just wedge obstacles. It's based on the work done by Lowen and his group. And what one sees is that there is an intermediate kind of angle of the wedge at which most of the particles or all of the particles are actually accumulated and jammed in that wedge. Otherwise, for small kind of opening angles or large angles, then there is a finite density of the particles outside or away from the wedge. So there is some interesting phase diagram of the system. And another example kind of related to the prior one is a system with some kind of a boundary with openings, and the boundary is made up of these wedges, basically. And initially, a colony of cells of bacteria is put in the system, and after a certain time, actually, most of the bacteria migrate to the right side of the system. So if there is no activity, of course, the particles will be distributed uniformly in the system. There will not be kind of a segregation between low density and high density regions. So that's a result of activity. Just because the particles it's easier, or the particles have an easier time going this way than going the other way. So there is a broken symmetry that is due to the geometry of the obstacles coupled to the activity of the system that is induced in the system. Another example of environmental effect is topological defects that are in the medium that is embedding the bacteria in this case. So the medium here is mainly water, but with a good amount of liquid crystal, and liquid crystal solution has some nematic order or smectic order that is induced by the two substrates confining the solution. And so you can control the type of order, the type of defects in the crystal solutions by the imprinted kind of structure of the substrate, which are static, not dynamic. So this kind of order of the in the liquid crystal solution is actually static. It's with some, of course, thermal fluctuations, not really dynamic. But if one has bacteria in this solution, then one observes that the bacteria acquired a collective vortical motion with a specific chirality that is determined by the type of defect of the liquid crystal. So in this case, we have a +1 defect, which looks like a kind of an attractor with the set circling around the +1. Of course, there are two types of +1 defects, and that implies that there are two types of chiralities of this vortical motion. And so if you have a system where you have +1 and -1 defects, then you can really kind of control and localize the motion of these bacteria. So they have created all kinds of defects in their liquid crystals, and can do quite a lot of varieties of controlled motion of bacteria in these systems. In another example, the behavior of this work is done by Marchetti's group, and I think Shankar was probably a student at IIT Madras here, if I recall. So what they have here is a solution of E. coli in a droplet, and but in that solution there is also a certain amount of DNA, and what they observe is that at low DNA concentrations, then the bacteria exhibit collective vortical motion that is unidirectional. It doesn't change direction. However, as the concentration is increased, then actually there is reversals in this vorticity, and the reversal seems to be quite periodic. Okay, so another study was performed on some type of environmental kind of situation where they controlled the substrates. And most of the work has been done on uniform substrates, of course. But what if you have a substrate that is patterned? So what they observe is that here you have a biofilm that grows much faster on the uniform substrate than on the non-uniform substrate. And the substrate here is such that the kind of direction of the grooves are kind of perpendicular to the direction of growth of the biofilm. And so the substrate structure affect the kind of collective behavior of these cells. So we will focus on the effect of pattern substrate on the collective behavior of self-propelled particles, and the work that, or this talk will be based on simulations. So the kind of the things that have to be included in the modeling, of course, is that we have self-propelled particles. We have to have that have tendency to orient themselves so their polarities parallel to each other locally, and of course one needs some interactions between the two particles. So point 1 and point 2 can be or are related. So there are different approaches that have been used. I don't think I will have the time to go through this. So the two main kind of approaches that have been used to look at theoretically the collective motion of particles are the so-called Vicsek model, which is probably one of the earliest ones, where you have point particles that move with constant speeds, and they have polarities. The orientation of the speed is along a polarity, and the polarity of the particle tends to be in the same direction as the polarity of the neighboring of the neighborhood, basically. And the other commonly used approach is so-called active Brownian particles, and that's what Chandan has talked about yesterday. So in this case, if the particles are just circular, then so the particles move according to kind of a Langevin approach with with an external force along a certain polarity or a certain direction, and that direction is determined by kind of rotational diffusion of the particles. So that is, and of course you have interactions between particles, and in this case if the particles are spherical or circular, then they tend to aggregate into domains where the motion is very low, and so you have what you call motility or mobility-induced phase separation. And these domains are not static. They can break up, they can be made, etc. They're very dynamical. But there is not much collective motion of the particle. They don't really move collectively unless you kind of make the particle anisotropic, then you would have collective motion of the particles. So the approach that we will that we have used is a very simple, I believe, approach in which a particle is modeled as essentially a ring polymer. And so you have monomers that are connected to each other, if you want. The particles interact via two-body interactions. They are connected by harmonic bonds. You have three-body interactions to control the rigidity. We introduce a polarity of these particles by controlling the preferred bending angle at the two poles of the particles, and we also control the area of the particle by just using some kind of compressibility, aerial compressibility term in the Hamiltonian. And we also make sure that these particles do not kind of overlap each other, so there is self-avoiding interaction that ensures disjointness of the particles. And this model, actually, we used it for looking at a passive problem of just the effect or the kind of the interplay between density and bending rigidity of these ring polymers on their structure in 2 dimensions. And one can see actually interesting structures, including triangular lattices and nematic as well as smectic phases as a function of density. So to make these particles active, we have to have a motility force, and the motility force is a function, is along the polarity. The polarity itself is really not a vector, it's just a kind of direction. So the direction of the force is determined by the angle between the historical velocity, kind of memory of the particle and the polarity. So if the angle is smaller than pi over 2, then the motility force is in this direction, otherwise it's in the opposite direction. And so, so there is some kind of memory time, tau m, and so this model allows for switching of the direction of the cells. And then the equations are solved as usual using kind of molecular dynamics with a Langevin thermostat with a driving force and some noise, kind of thermal noise, if you want, added to the equations. So in the case of a uniform system that is without any constraint, then one sees the usual kind of collective behavior that depends on the driving force. The higher is the driving force, the higher is the amount of collective behavior in the system, and that was quantified by, for example, the average cluster size as well as the cluster size distribution. So for low driving forces, the cluster size distribution is just an exponential decaying function, but for high driving forces, then you have a power law behavior that may, and then you may have a peak or a shoulder in the distribution, which indicates the tendency of having giant clusters in your system. Actually, this is just a comparison with the data that we have, and the power law of the cluster size distribution with experimental values. So you see the same behavior and the same power law, etc. So the model is nice, despite its simplicity in kind of looking at collective behavior. So and we looked at also, of course, the ordering of the velocity field as well as the nematic field, that is the polarity field. And one sees that there is, of course, order induced in both when there is collective motion, but the order of the velocity field is actually quite high, about more than 2 times that of the nematic field. So there is order, but there is a higher alignment of the velocities of the self-propelled particles than actually their polarities. So I will, I think, just jump to the system where we have circular confinement as well as a substrate that is patterned. And we consider a situation where the substrate is patterned within a certain radius that is smaller than the radius of the system. The interaction between the wall and the particles is just repulsive, and the interactions between all particles is repulsive. Actually, there is no tendency to aggregate at equilibrium. And the effect of the substrate is, think of the substrate as made up of concentric grooves, and the particles just tend to be guided by the grooves. So what the substrate does is induce a torque on each particle that tends to align the particle tangentially with the grooves. That's basically the interaction between the grooves and or the substrate and the particles. So this is just a case where the substrate is uniform. There is no grooves, if you want, and the driving force is not actually very high. So there is some collective motion, but it's not really tremendous. And as the driving force is increased, then there is a higher amount of particles that aggregate to kind of at the boundary, some kind of collective motion, and some depletion or less particles in the middle. So that relates to the first example I showed you about particles, active particles in a circular confinement. The same behavior. So now, if we have a substrate, then one sees that this is the same driving force, except that the substrate in that light blue region is patterned, and one sees that there is a collective motion of the particles within that region, and that collective motion is clearly vortical, right? And that vortex seems to be kind of unidirectional. The chirality doesn't change. And this is an example, 2 examples of a system with a low driving force and a high driving force at same Parking fraction of the particles. And one sees that first of all, there is this interesting depletion that appears in the middle of the system. So the particles avoid going to that very center of the system. The size of the depletion region decreases with the increase of driving force. And of course, there is a higher accumulation of particles in the outer boundary of the system. So the coupling of the driving force with the interaction with the substrate certainly induces some interesting collective motion in the system. And what is also interesting is that for a certain kind of range of driving forces, there are 2 vortices actually. There is a vortex inside the pattern region, and there is also a vortex in the right next to the wall. The directions of these vortices can be the same or can be different. Oops. Okay, so I don't know how to run that movie, but so the vortices in the core and outside in the uniform region can be in the same direction or in opposite directions. So we calculated the some order parameter, vortical order parameter, to look at how the particles, or the kind of order, the kinetic order of the particle, if you wish. And so this vortical order parameter increases sharply at some driving forces. Whether there is a phase transition or not, this doesn't look like there is really truly a phase transition, but there is a sharp increase. And the red curve corresponds to the case of a uniform substrate, whereas the blue one corresponds to the case of a substrate that is patterned. Of course, the degree of vertical motion or order is higher for the case where the substrate is patterned. So particularly the onset, if you want, of vertical or collective motion happens at a weaker driving force when the substrate is patterned than when it is not. Another interesting aspect of the vertical motion in the for intermediate values of the driving force corresponding to this green region, there is this kind of bifurcation of the if you want, chiralities of the vortices of the sets. So when the chiralities are opposite, of course, the order parameter would be small, and that's why you have this low branch. Otherwise, there is this high branch. This vertical order parameter increases, of course, as expected, with the strength of the interaction of the substrate with the particles. So this just kind of an understanding of why there is this vertical, kind of reversals in the vertical motion of the inner core, just because outside in the uniform region, besides the vortex that is right next to the edge, the particles in between are moving collectively in clusters, but are not necessarily moving in as a vortex. And these clusters from time to time collide with the vortex in the patterned region, and when they do, depending on the size of this cluster, that can perturb the inner cluster and change its direction. Now this just shows the density profile, the distribution of the particles radially from the center of the system. And so there is this depletion zone that I will talk about. Then there is a region which is kind of where there is a high amount of particles right before the boundary or edge of the patterned region. Then there is a reduction. Of course, again, you have the accumulation near the outer wall of the system. So to understand the source of this depletion zone, we just considered a single particle in some patterned region initially near the center. And what one sees is that the particle actually moves in a spiral fashion and outward fashion. So the combined effect of the torques induced by the substrate and the driving force on the particle is to effectively move the particle outward, actually. So the substrate pushes the particle outward, outside the substrate region. And those are just trajectories of the single particles depending on the driving force and the strength of the interaction that they have with the substrate. So that was for the depletion zone. What about this high kind of region with high density of the particles? So it's clear here that the particles in this vortex are highly dense beyond that depletion zone, and then you have a weaker or a lower amount of particles outside in the uniform region. So what is the reason for this kind of non-monotonous distribution? So one way to understand that is to look at the kind of fluxes of particles through the edge of the patterned region. So particles will go in, of course, and go out, right? And at steady state, if you want, the outflux of particles from the patterned region should equal the influx of particles to the patterned region, because the system is at steady state. And so these fluxes are just proportional to the speed, the kind of the normal speed. Is it 5 minutes? So the flux is proportional to the normal speed of the particles, or rather normal velocity of the particles, and the local density of the particles in the patterned region and in the uniform region. And of course, if you look at the normal speed of the particles, the particles in the substrate are moving mostly in a kind of tangential fashion, then normal speed is actually relatively weak. So the normal speed of the particles in the patterned region is actually lower than that in the uniform region. So the higher radial speed here, for smaller radii, is because of that tendency of the substrate to push the particle outward, as I discussed earlier. So because you have this kind of mass balance, and because the velocities are not equal, the normal velocities are not equal, then the density of the particles in the patterned region has to be larger than the density of the particles in the uniform region. Okay, and we could confirm that by taking the case where we don't have actually a circular boundary, but rather, let's say, periodic boundary conditions with a patterned circular region as before. And in this situation, actually, we see that there is a higher amount of particles in the patterned region than with the kind of circular outer boundary. And the reason is because that our influx of particles, this purple arrow, if you want, is coming from particles from the, of course, from the uniform region. Now, if you have periodic boundary condition, particles can go in both directions. They cannot only go towards the patterned region, and so you have fewer particles. So you have fewer particles in the, if you want, fewer particles or a smaller. You have actually a higher flux. You have a higher flux because the particles that leave this region are going back through the boundary condition. So actually you have a higher amount because you have less accumulation of particles at the boundary. So you have more particles incoming towards the patterned region, and therefore that requires a higher amount of particles in the patterned region near its boundary. So the last thing I will talk about is these reversals in the vorticity at high densities, where you have, if you want, a situation where you have full confluence. There is no empty space in the system. And in this case, we see that intermittently there is actually reversals in the direction of the overall vortex, and that these reversals are initiated or come from the center of the system. They always originate from the center of the system. These reversals happen only at high densities, and that's what leads to reduction in this vortical order parameter, because you have particles moving in different directions. Otherwise, there is no reversals because there is a depletion in the center of the system, and therefore you cannot have this reversals in direction originating from the center. And if you look at the rate of these reversals as a function of density, it increases, and that's what this kappa is about, as a function of Parking fraction of the particles. What happened? All right, so I'm sorry, something wrong happened. And I'm about to finish anyway. So the system just seems you have that. Oh wait. So there is a slowing down in my system. It doesn't seem to respond and it's all over the place. Yeah, by that time, the next speaker will have to start, right? Okay. Yeah, I will. My apologies. Yeah, so I think this is enough because that's what I want to kind of end. So this is just good Lord. I guess I will have to stop. Okay, let's hope, cross fingers or pray or whatever is your preference that it doesn't go wrand. So this just shows the overall vertical, actually the vertical order parameter in some band within the system as a function of time, and it shows this kind of interesting reversals at relatively kind of high but not very high packing fraction of the particles, and this is at high packing fraction. And so you can see visually that these kind of reversals become more or less periodic. And actually, we calculated the kind of power spectral density or power spectrum as a function of, as a function of frequency, and you see that there is an emergence of a very well-defined peak at high packing fractions, which indicate that these reversals become kind of quasi-periodic. That peak is not the kind of intensely sharp, that are not really truly periodic, but they are quasi-periodic. So we do not have a really very clear understanding of how these reversals happen, but we looked at the amount of fluctuations in the tangential velocity of the particles in different regions of the system. So the black region is very close to the center, and the red corresponds to the region in the outer kind of part of the system. You see a huge amount of fluctuations in the center. So actually the motion particles in the kind of center of the system is quite turbulent. It changes a lot direction, and from time to time, kind of there is nucleation of a vortex that is of opposite direction and growth of that vortex. So I will just stop here. In conclusion, we have a relatively simple ring polymer model of self-propelled particles that we believe is useful to look at various problems of collective behavior of systems. The model, the good thing about this model is that it accounts for flexibility and anisotropy, of course, self-propulsion, but also area of the particles. So these are not point particles, they are not hard disks, they are really flexible particles with very well controlled area. If in the case of a uniform substrate, you see the usual collective behavior, clustering, and collective motion of of the particles. And when there is a substrate that is patterned, then one observes this interesting collective motion that is vortical, and we have vortical kind of chirality reversals of the vortices, and as well as quasi-periodic vorticity reversals at very high packing fractions. Now, I think there's a lot we can do with this model, and we are looking at various things where probably we can look at things that cannot be looked at with other approaches. Numerically, this is a very efficient model also. It's very easy to do the simulation. Thank you.
The outer region, right, in the case of patterned surfaces, you still had particles sort of clustered and moving tangentially to the outer boundary, right?
Yes.
So
yes.
What is the mechanism that leads to this, high concentration and tangential movement?
So that is observed in many systems, and I think Sheldon talked about that. So you have particles that, that are motile and are incoming towards the edge. They can't go further. They just orient parallel to it and keep moving. That's basically it. So there is a broken symmetry caused by the wall in the direction of the particles, and that's what causes aggregation of the particles at the boundary.
And they still move in the tangential direction.
So if the density of the particles at the edge is not high, that there is gaps, then you don't have a unidirectional vortex. But if the driving force is high enough and there is enough particles, then you have a complete kind of ring of particles with many layers maybe, and those particles actually will have typically the vortex will be unidirectional. Yeah.
How does the direction reversibility get affected by the size of the system? So how long does it take to reverse if it becomes a very large system?
Yeah, so that's a good question. I don't think we did look at that carefully, but that's a good question. And I think the system size here plays an important role, just like Sheldon's system yesterday. And I think there will be an effect there, yes. And also not only the system size, I think the size of the patterned region as well. That will play a role, yes.
So one question is about the use of rings. Instead of rings, if we had just polymer segments, would you see the same thing?
Well, I haven't done that, obviously.
Yeah.
That's a good question. So like Gumper and others have looked at the collective motion of ring polymers, flexible and semi-flexible. So the thing about rings is that there is no area really, that they are not really fat in a way. They're very long. Yeah. And some bacteria.
I showed a slide of that. There were just basically nails, which are sort of sitting on a bed of small spherical particles. And then if you vibrate them, then they have this kind of motion along the edge.
Right, right. Yeah, around the edges. So that's most probably very similar. I mean, this system, there is no hydrodynamics in this system, so would.
Yeah, I guess if it's a rod, it'll do the same thing. But the difference is here there is no the particles are not really polar, actually like pneumatic-like.
Mm-hmm. In that experiment, the
probably more like Brownian particles.
Mm-hmm. And the last part, one thing. I mean, when you see these two kinds of motion, in one case the two polarities are different. In one case, they're in the same. So that is determined by initial conditions. I mean, no.
No. I mean, there is because you can average over time. There is a lot of things that happen over time. The initial condition is, I think.
I see. So I mean, you can see spontaneous transitions between these two cases. That one case where the inner and outer boundary have the same direction, and
so that other parameter was what. So we right?
Mhm.
And so we have kind of carefully taken part where all the parameters are going the same kind of direction
Mhm.
or opposite direction.
Direction,
and
yeah.
evaluated
Yeah.
overall all the parameters involved.
Right. And I guess there the sample size dependence of this time scale might be of importance. I mean, the switching happens over some time scale.
Right. So there is that kind of memory time you're saying of the driving force.
No.
Oh,
Just the spontaneous switching.
okay.
So
So there
that-
is a time scale.
there is a
Okay.
time scale
I mean,
associated with that.
We didn't also look at that time scale as we did for the kind of the vorticity reversals at
Mhm.
high density. But I think that there is a second time scale. The problem is that these reversals within the simulation time don't happen that often.
That frequently,
And so
yeah.
it was very hard for us
Mhm.
to kind of quantify this time scale.
Okay. Thanks a lot.
Thank you. Okay, so I think we should wind up this session now. Thank you very much, Professor Laradji.